The next module we will discuss about this conducting polymer based actuation and a stick slip based system. So, as far as this conducting polymer based actuation is concerned, so there are wide varieties of polymers which have been demonstrating this actuation mechanism. One of the polymer which is efficiently used is called as an electroactive polymer. See, these electroactive polymers are inert materials that can deform up to 300% of its initial shape, and it has a capability of generating large force compared to the strength of the human muscles. So, of course, since it's a polymer, it almost has a capability similar to the human muscles, so that these kind of conducting polymers are efficiently used for such kind of applications. Now, when we try to classify this electroactive polymer, so these electroactive polymers are classified into two. One is called as an ionic polymer and the other one is called as a conductive polymer. So, as far as these ionic polymers are concerned, so these are kind of polyelectrolyte polymer which are kind of integrated with metallic particles. So, these metallic particles, when they are integrated with electrolyte based polymer, it has a potential application towards actuation. However, with reference to this particular conductive polymer is concerned, we have a polyacetylene which is being captured or which is being used for different applications. Now, let me just introduce you to this conducting polymer based actuation. So, as far as this conducting polymer based actuation is concerned, this is an exciting field where a special material can change the shape when electricity is applied. It almost works like a muscle work. However, in the case of a conducting polymer, it exhibits an electronic conductivity, making them unusual amongst the organic materials. So, these are wide varieties of chemical structures of some conducting polymers, which is like polyaniline, trans polyacetylene. So, this cis polyacetylene and polypyrrole are some of the different conducting polymers which are being efficiently used for a kind of a micro robotic applications. Now, when we try to look into the basic principle of actuation, these conducting polymers can easily lose and gain electron when voltage is applied. So, when it is immersed in a medium containing ions, they will attract or repel certain ions. This will expand or contract after this exchange. This property can be exploited and they can be used for a kind of a actuator, basically for micro actuations. Now, like some of the unique property of these conducting polymers are a defining structure of a conducting polymer is their conjugated backbone, which enable them some degrees of electron delocalization and hence it is for an electronic conduction. Now, there is a process of doping which involves the addition or removal of charges from the polymer chain, resulting in structural change and creation of states in a band gap. So, the doping process also produces a volume change. These dimensional changes are used to perform mechanical work. Thus, actuation in conducting polymers are derived from a dimensional change associated with the change in the polymer oxidation state. Now, when we try to look into the overall mechanism of these actuations, the way these actuators work is mainly through a process called ion doping and dedoping. That is, when you apply a voltage, the polymer either gains or loses an electrons as discussed before to balance this. These ions, these tiny charged particles move in and out. This can make the polymer expand or contract. So, there are two main types of configuration of this configuration or mechanism which persists with reference to actuation. One is called as anion driven, which is a small ion enter or leave, causing the polymer to grow or shrink. Second one is called as a cation driven. It is a large ion stay put and other ions move in, leading to a expansion or contraction. Now, when we try to see the history behind the operation of this actuator, So this conducting polymer was first discovered by a person called Shirakawa, Alan Hager. So they were awarded for a Nobel Prize in chemistry for this discovery for the development of conducting polymer. That is, like, accidentally this this invention happened accidentally, that when the conducting polymer was kept near to a kind of a when a polymer was kept near to a kind of a furnace, so because of heating they could activate the electrical behavior of this polymer, and later this has resulted in a kind of a conducting polymer for the system. So if you closely observe in these conducting polymers, so these conducting polymers has a capability to actuate, it can hold the system and it can relieve the system. So like when there is an electrical contact is applied to it, by actuating it, so it can actuate at different dimensions. So appropriately, like similar to shape memory alloy, here also a kind of a shape setting needs to be incorporated. So this shape setting has a capability to generate a kind of a shape. Okay. So the interesting part of this conducting polymer is these conducting polymers can be actuated in any kind of medium. In fact, that's how this has opened up a new domain in such a way that, like for in the case of underwater manipulation or in the case of underwater explorations, such kind of conducting polymers can be efficiently used for handling some of the organisms or handling some of the materials in an underwater condition. Now, when we try to look into the fundamental principle of actuation in the case of a conducting polymer, the electrochemical doping and the electrochemical de-doping process exhibits. So the actuation mechanism in conducting polymer is primarily based on the electrochemical doping and a de-doping process. So when an electrical potential is applied, the polymer undergoes oxidation or reduction, leading to changes in its electronic structure. Now there are two different configurations which exist. One is called as a volume change and another one is called as the conformational shift. As the polymer is oxidized or reduced, it experiences volume change due to the insertion or expulsion of ions and solvent molecules. These volume changes are accompanied by a conformational shift in the polymer backbone. When we try to talk about the ion migration and solvent interaction, so the doping process involves the migration of ions between the polymers and the surrounding electrode. This ion movement along with the associated solvent interacts play a crucial role in the actuation mechanism. In fact, you might have heard a lot about this osmotic effect. This osmotic effect causes a solvent molecule to move into the polymer in a number far exceeding those bounded in the solvation cell of the mobile ions, resulting in a significant volume, thus leading to a kind of a structure what we are looking for. So when we try to observe the different types of conducting polymers, commonly there are two different types of conducting polymers which exist. One is called as polyaniline, which we call it as PANI, and the other one is called as polypyrrole. These polyaniline and polypyrrole are some of the key conducting polymers which are used in micro robotic system. So polyaniline is one of the most studied conducting polymer due to its environmental stability and simple synthesis process. It exhibits a good electrical conductivity and electromechanical process, make it suitable for actuation applications. With reference to polypyrrole perspective point of view, polypyrrole is widely used in actuator research due to its high conductivity, good environmental stability, larger actuation strain, and it can be easily synthesized through a chemical or a electrochemical method. Similarly, there is a kind of a conducting polymer called P-dot, which is poly 3,4-ethylene dioxide thiophene. So this P-dot, especially when it is combined with poly, that is styrene sulfonate PSS, to form a P-dot PSS. This P-dot PSS has gained an attention in the recent years. It offers an excellent conductivity and transparency and processability, making it suitable for various actuation applications. So these are some of the advantages of using this P-dot PSS, and utilization of these P.PSS for different applications. Now, let us discuss about the various actuation mechanism which exhibits for actuating these conducting polymers. One is called as a electrochemical actuation. So, electrochemical actuation is the most common mechanism in conducting polymer actuator. So, it involves the application of an electrical potential to induce redox reaction leading to ion movement and volume change. The next one is called as a electrothermal actuation. As far as this electrothermal actuation is concerned, some conducting polymer actuators can be activated by a joule heating. That is, when an electric current passes through the polymer, it generates heating causing through thermal expansion and contraction. So, by supplying a heat to it, so appropriately a thermal expansion and contraction happens. Then the other process is through called as photo-induced actuation. So, photo-induced actuation, as the name suggests, that like what we can do is we can use a light. So, the light can be efficiently used, or the light can be absorbed by these conducting polymers, and appropriately there is a kind of an actuation which persists. So, like certain conducting polymers can exhibit actuation response to the light stimuli, and this mechanism is less common but offers a potential for a remote actuation in specific locations. In fact, a similar case study we had seen in the earlier case also, where a laser is used for actuating the shape memory alloy for an appropriate motion or appropriate propulsion. Now, some of the key properties and characteristics of these conducting polymers are concerned. These conducting polymers are kind of a strain and stress generation. That is, conducting polymers can generate strains typically in the range of 1 to 2%, with some advanced system have achieving higher values. As far as response time and frequency perspective point of view, the response time of the conducting polymer actuator is generally in the order of seconds to minutes. Depending upon the size and configuration of the actuator, the actuator speed is often limited by the rate of ion diffusion. Now, when we try to talk about the efficiency and energy density of these conducting polymers, the energy density of the conducting polymer actuator is compared to that of the a mammalian skeletal muscle. However, their efficiency is typically low, often less than 1%. So which means that it has a higher energy density and it has a potential application towards biomimicking related areas as well as biomimicking related domains. However, with reference to efficacy perspective point of view, it is very less. Next important aspect with reference to usage of conducting polymer for micro robotic application is the cycle life and stability. So, improving the cycle life and long-term stability of a conducting polymer actuator remains a significant challenge. Current system can achieve close to around thousands of cycles, but degradation over the time is still a concern. Now, let us see some of the different device architectures of this conducting based polymer. One device architecture is called as a bilayer actuator. The bilayer actuator consists of a conducting polymer layer bonded to a passive layer. When the polymer layer expands and contracts, it causes bending of the entire structure. So, there is a kind of a conducting polymer and a host matrix which is available. So, and then it is connected to the anode and the cathode. So, what happens is, like when we try to give a biasing to it, there is going to be a bending in the system, and when we try to actuate it, it comes back to its shape. Similarly, so it is almost equivalent to a kind of a biomorph system which we had discussed earlier for shape memory alloy. That is, the actuation of the actuation of the system is taken care by the conducting polymer for bending. However, the host matrix acts as a kind of a support structure, so that it participates in the actuation, so that when there is a return stroke is happening, this host matrix will participate and it will return and it will ensure the return stroke. Next, we have a kind of a tri-layer actuator. So, the tri-layer actuator typically comprises of two conducting polymer layers separated by an electrolyte containing layer. This configuration allows for a bidirectional actuation. So in this bidirectional actuation, if you see the overall configuration of it, there are two conducting polymer layers are available over here, and then in between we have a kind of a host matrix which is available. So what is happening is, when we try to actuate this host matrix, so like one is being trained to actuate in this direction and the other one is trained in the other direction. However, the host matrix acts as a buffer layer in such a way that it will try to compensate both the actuation in the positive as well as in the negative direction, or I can say it can support the actuation in both the directions. So that's how it can work upon. Now, when we try to talk about the application of these conducting polymer based systems, these conducting polymer based systems are efficiently used for a kind of biomedical applications, like especially in conducting polymer actuators are being explored for use in minimal invasive surgical tool, drug delivery and an artificial muscle for prosthetic. As far as soft robotics is concerned, it has a potential application. It has a high flexibility and biocompatibility of conducting polymer actuator, which makes them attractive for soft robotic application, including grippers and locomotion systems. Microfluidic perspective point of view, conducting polymer actuator can be used as valves and pumps in microfluidic devices, which offers a precise control. Like say in the case of microfluidic chip, so appropriately we can have a control over the actuation. Now, with reference to future direction perspective point of view, like it has an improved actuation performance. There are various ongoing research focus on enhancing the strain, stress and response time through the material optimization and novel device architecture, like either working on the chemical bonding or the behavior of these conducting polymers. There are some research which focus upon the training of these conducting polymers for different applications. So there are some explorations where the conducting polymers are actuated through different domains, including magnetic, electric, light, heat and moisture. Enhancing the long-term stability, that is improving the cycle life and environmental stability of conducting polymer actuators remains a key area of research. As well as novel fabrication technique perspective point of view, these advanced manufacturing methods such as 3D printing of conducting polymers are being explored to create complex structures. Let us see some of the conducting polymer based actuation. In fact, this is one shape memory alloy based polymers which are being created. So initially this is a kind of an initial shape. It is being deformed by an applying stress, and then like the PLA starts. So here the PLA is integrated into it. So and then it regains the shape. So this is almost kind of a PLA coupled with the shape memory alloy polymer. So what it tries to do is we are trying to deform it, and by a hot water actuation we can regain its original shape. So like almost the hot water is in the range of 60 degrees, which is quite enough. In fact, for a micro actuation perspective point of view, small micro cantilevers can be fabricated using this particular technology, and these particular technology can be embedded appropriately in such a way that by using a hot water spraying we can go for a selective actuation. Like for example, if this is a kind of structure is there, and by spraying and hot water actuation we can appropriately displace to get the structure. These shape memory alloy polymer are polymeric smart materials that can be deformed later, and it can be actuated through an external sim line. This is an interesting conducting polymer which is called as Electromagnet Rheological based fluid based conducting system. So in this electromagnetical, so what we are trying to do is like the electromagnetic rheological fluids and magnet are smart, consisting of electrically and magnetically polarized particle which are suspended in the non conducting fluid. So ideally these are called as a electromagneto rheological systems. So what happens is, So in this fluid, the particles are dispersed as shown over here. When a voltage is applied appropriately, it tries to take a shape. So when it tries to take a shape, it aligns in a particular domain, so that this alignment will be capable enough for it to make it to move it in a particular direction, and then this can be used for different applications. Like in fact, there is a ferrofluidic structures which is like micro robotic ferrofluidic structure. If you search in YouTube, you will get a kind of a structure. So this structure is something like a complete nanoparticle will be dispersed in the liquid medium, and then a kind of a fluctuating magnetic field will be applied. So these fluctuating magnetic fields are capable enough in such a way that it will try to energize and it will try to align these ferrofluidic structure, and finally it form a kind of a sculpture kind of arrangement. So as far as in this ferrofluidic structures are concerned, so these are efficiently used for micro robotic applications, especially by giving an external actuation. You can align the nodes and appropriately you can use it for the kind of actuation behavior, or in other words, it is also used for damping related applications. For instance, so this is a kind of a like a biological wall. So in this biological wall, so inside this biological wall, the liquid is made to pass through it. Okay, so this liquid contains this certain amount of these solid structural material, which are called as like electro or magnetorheological particles. So these electro or magnetorheological particles is made to flow through this particular tube, and now when it is made to pass through this particular tube, and let us consider there is kind of obstruction which is available over here, and this obstruction needs to be removed. So the mechanism can be deployed in such a way that an actuation field can be applied. This actuation field will induce a certain amount of structure, something like this. So this structures can be actuated, so it acts as a kind of a drilling unit, or it acts as a kind of a grinding wheel, so that it grinds the fatty content or a kind of a solid content which is available, and then it can be completely eroded and it can be flushed away along with the system. So such kind of biological related applications can be deployed using this magnetorheological. Of course, in the biomimicking as well as in the micromanipulation related to biomimicking, so we will be discussing a lot about this with different case studies. Okay. Overall, so we had discussed about the conducting polymer, about the different types of conducting polymer, the capabilities of these conducting polymers, the classification of these conducting polymers, and the overall basic principle and actuation which are involved against these conducting polymers, the unique property of these conducting polymers, and the mechanism of actuation. So we have also discussed about this characteristics of these conducting polymers, about the fundamental principle of actuation against the conducting polymers, and there are common types of conducting polymers which are there, which is used in actuation, like polyaniline, polypropylene, and P.PSS, which are available, and different actuation mechanisms are deployed, which includes electrochemical reaction and electrothermal and photo-induced reactions which are being deployed. And then there are different key characteristics which passes, which includes a stress generation, response, efficiency, and energy density, etc. There are different device architectures which are being established using this conducting polymer, like it's a unimorph base and it is a kind of a bimorph base systems which are being well established using this conducting polymer technology. The conducting polymer has wide range of applications, which includes a biomedical device, soft robotics, microfluidics, etc. So it has quite a good amount of future directions with reference to actuation, with reference to longer term stability and with respect to novel fabrication techniques. And then this is an example of how conducting polymer based actuations are being done. In fact, here a PLA is taken and appropriately it is being taken up. Other sets of such kind of smart actuators, which includes a magneto-rheological based system. So these magneto-rheological based systems are kind of fluid or gel based systems which is being integrated into the environment or in the domain, and appropriate actuations are deployed to get the different characteristics behavior. So now we will discuss, let us go to the next part, which is a stick slip, which we will be discussing in the upcoming classes. We have discussed a lot about this shape memory alloys. In fact, we have discussed about how the different locomotion of this shape memory alloy exists and what are the different configurations of shape memory alloys, etc. Now, like as far as these, whenever we are trying to consider these shape memory alloy micro actuators, there are certain design principles which are there. So if we try to correlate the design principles, so it will be efficient enough so that we can use it for different application, including the locomotion related to like pick and place arrangement or related to feeders, etc. So let us discuss some of the configuration related to this SMA design principles. Like one of the important configuration is called as a bias spring based configuration. So in this bias spring configuration, some time of intuitive approach to use a mechanical element that constantly supplies force on the material. So this mechanical element can be either a kind of a bias spring or a kind of an antagonistic design or a dead weight. So let us see how does the configuration looks like. So in this configuration, let us consider this as a bias spring, and this is a kind of a shape memory alloy which exists. Now, so in this particular configuration, like this is called as a bias spring. Let me just represent it as BS. BS is nothing but the bias spring, and this is the shape memory alloy. So here, this is a kind of a fixed structure, and del is a kind of a deformation behavior which moves. So in this particular case, now we can have two different conditions. One is when T is less than martensite finish, then we can have the expansion with reference to bias and with reference to SMA, so that it reaches this particular point. Now, like in addition to this, this condition can be deployed in both cases. One is when T is less than martensite finish and when T is greater than austenite finish. So in both these conditions, we can exhibit this structure. So only thing is there will be a kind of a cycle between heating and a cooling behavior. Now, as far as in this particular case is concerned, so the system consists of a bias spring and the SMA is pre-strained by a deformation del attached at both the ends, so that the system remains in a deformed state after mounting, and this deformation induces a reorientation of martensite variant. So the equilibrium point in this is found to be looking for an equilibrium between the force applied by the SMA and the force resulting from the bias spring action. So upon heating, the material tries to regain its original shape. Martensite turns into austenite, resulting from an increasing force towards the SMA spring, which we call it as state 2. So on cooling, the martensite variants nucleate, but instead of being homogeneously distributed as it would happen in the case of free stress cooling, they orient themselves so that the stress resulting from pulling force applied by the spring on the SMA is minimized. As a consequence, the equilibrium shift towards the bias spring is at this time. So like in order to find this, like there are different methods which are available. So one method, in fact, we had also demonstrated, like we have a kind of a Michelson's interferometer. Using a Michelson's interferometer, we can calibrate the spring. So we can study the overall fatigue life behavior of the spring. So some of the key aspects when we try to observe using this configuration is the maximum stress the system will experience upon the shape recovery depend on the amount of preloading and the stiffness of the bias spring and the SMA used. Similarly, one more aspect is the stress versus temperature rate will depend upon the stiffness ratio between the SMA and the bias spring. So this is one configuration. In fact, these kind of bias spring are effectively used in certain amount of valves, etc. So in fact, I can just show you one simple configuration. Let us consider this as a kind of an poppet valve. So in this poppet valve, there are two configurations are there. So in this configuration, we have an arrangement where there is a spring is available. This is a kind of a bias spring. And then we have a SI poppet in place. So we have a control pressure and fluid in, which is being integrated over here. So, and then there is a kind of a fluid orifice kind of arrangement. So this fluid orifice will take care of the overall modulation between the structures. Okay, so this is one configuration which is called as a bias spring based configuration, and the other configuration we also call it as a antagonistic configuration. So in the case of an antagonistic configuration, we will be having two shape memory alloys. So this is shape memory alloy 1 and shape memory alloy 2. So there will be a set of configuration in such a way that whenever we need to have an expansion in this direction, so the variant will be a kind of a simple bias spring actuator principle where it uses two shape memory alloy elements. So it consists of mounting two SMA actuator opposite to each other. As for the bias spring, the system consists of two coupled actuators is first pre-stress. So both the actuators are deformed. So these are SMAs. From their parent phase shape, during this step, when an actuator transforms, it deforms its counterpart. So by heating alternatively, the two actuator, a sequence of deformation and recovery is introduced, lead to a kind of a reversible motion. Although the working principle is relatively simple, such linear actuators have highly nonlinear characteristics. So the behavior can be seen from the phenomenon of pneumological point by examining the characteristics. So basically, wherever we require a large motion and amplitude, such kind of antagonistic configurations are introduced. Next, we have a kind of a SMA bimorph based configuration. So as far as this SMA bimorph based configuration is concerned, so we have a kind of a in this SMA bimorph configuration, we have two SMA structures. So one is a kind of a smart material, other one will cater the overall deformation which exhibits in this particular structure. So like we have seen this combinations where it is in such a way that like when we try to actuate the shape memory alloy, the shape memory alloy gets actuated, and then there is going to be a polymer structure. This polymer structure will also get actuated along with the shape memory alloy. When we try to cut off the heat, it comes back to its shape. In fact, just to give you a better understanding, let me just show you the overall mechanism of stress generation when a shape memory alloy is deposited on a silicon wafer. So let us consider. So there will be a kind of a different phase regime which exhibits. So this is a kind of a Martensite behavior. So if I try to map it with reference to the stress and with reference to temperature, this is the sigma max and sigma d. We have the Martensite phase over here. This is a kind of a phase transformation regime. And this is the bimorph regime. So, and this is the austenite phase. We have an annealing, and this is the temperature for annealing. And this is the kind of a crystalline material which exhibits. So when we try to illustrate this figure, this is a kind of an NITA film is deposited on an SI substrate. At the deposition temperature considered, the film is amorphous, no crystallographic structure is formed. To be functional, an annealing step is required, which is realized by heating the film, typically by 700 to 900 Kelvin. Upon heating, due to the difference between this transformation film and the substrate, a compressive stress gets built. So upon crystallization at a temperature TA, the stress is relaxed and the film is under tensile on cooling. So in the device operating mode, the biasing stress can be effectively used to deflect, for instance, an SI cantilever beam or a membrane. So like this can be used for a kind of a micro gripper arrangement. For example, if this is a kind of a micro gripper arrangement, and here we have a bimorph kind of structure. So what happens is the actuation can be appropriately we can give a biasing appropriately to get the required actuation. So that is one advantage of this system. So we can encash a kind of a one-way effect, and then we can create a kind of an appropriate displacement using this structure. Next concept is kind of a two-way effect. In the case of a two-way effect, so we have a kind of a monolithic kind of structure. So it is something like this. You have a single structure. And one way of actuation is happening in this direction, and the second way is happening in this direction. So this kind of two-way effect can be effectively used or effectively deployed using this system. So in addition to this, there is one more design principle which is available, which we call it as a kind of a monolithic base structure. In the case of monolithic base structure also, so this will also deploy the similar concept. In the case of monolithic structure, what happens is like we are using a single system, and these single systems are appropriately fabricated to get the structure. So the actuating properties of the SMA originates from particularly from the crystallographic transformation, and that takes place when the temperature is varied. So the crystallographic transformation can only make if the material is crystallized. So the crystallization of the material is achieved by heating the material at high temperature, typically in the range of 500 to 800 degrees Celsius after forming process. If the annealing step is not conducted, the proper crystallization will not be present, and consequence and the material will not exhibit a shape memory property, but it will behave like a kind of a conventional metallic material. So when we look into the concept of this monolithic integration in SMA consists in performing the annealing step only locally rather than in the complete device volume, and to use the combination of the annealed and the non-annealed zone to perform the actuation functions. To so it is something like this, assuming we have only 1 or 2 springs. So like for example, in the case of a monolithic structure, of SMA, let us consider this is a kind of an annealed structure. This is a kind of a non-annealed. So this is a kind of SMA spline kind of structure. So we are manipulating the crystallization appropriately to get the required displacement. In fact, higher order, in order to take care of the precise control, here the actuation is through a thermal. We can also use a laser. So when we try to irradiate with the laser, appropriately we can have a precise position of the system. So these are some kind of configurations which are available, which are there for creating these monolithic kind of structure for SMA related application. Of course, there are wide combinations of or various configurations of SMAs which can be effectively used for micro robotic related applications, which we have seen and we will be seeing in the biomimicking as well as in other robotic structures.